from the Brazilian, good afternoon, for the Netherlands. Yeah. Here we have a pleasure to receive in our online conversation with Dr. Joris van der Velden. Sorry if I didn't have the nice pronunciation of your name. But we are here to discuss a disruptive innovation from the enterprise MX3D, because this innovation, this bridge, is a large innovation in the printing 3D extruders. We are proud to receive you in our meeting, and I give it to Rodrigo to continue the introduction of you. Thank you, Dr. Joris.
Thank you, Nelson.
Okay.
Yes.
Thank you, Nelson. Okay, thank you, Nelson. First, I'd like to tell our attendants that you can send us questions here using the chat during the talk. Some of them will be selected and read after Mr. van der Velden's presentation. Well, now I would like to introduce our guest. Joris van der Velden leads MX3D since the birth of the company in 2015. He also held the general management position at Joris Laarman Studio. MX3D became worldwide known when 3D printed a 12-meter, 6-ton steel bridge for the city center of Amsterdam. 4 industrial robots 3D printing stainless steel simultaneously were used. The technology for this project was auto-developed by the company. The bridge has also been instrumented with an innovative sensor system. The goal is to develop a digital twin of this bridge, a complete digital model of the bridge. MX3D won several prizes in the last 3 years, such as the prestigious Start Prize awarded by the European Union, the Dutch Design Public Award, the Dutch Chamber of Commerce Top 20 Most Innovative Companies, Top 10 Most Promising Robotic Startups by EU's Robot Union Program, a 3D PC Award, a GeoBeam Award, and the Dutch Design Week Public Award. As you can see, we are receiving here today really an eminent professional of a world-renowned tech company. So now please, Mr. van der Velden, directly from Amsterdam, give your talk.
Thank you for the kind introduction, and it is indeed a nice list of awards if I hear it back like that. But yeah, so that's all an achievement of the last 6 years MX3D. Maybe to start immediately with one correction, I'm not a doctor actually. I'm not even an engineer, and this is probably one of my first sort of lessons in this presentation, is that that innovation sometimes comes from unexpected angles. So here you have an engineering 3D printing company led by a lawyer who studied international humanitarian law. So everything is possible as long as you have a vision and are able to find the right bright minds around you that are actually able to make such innovation possible. So here you see the bridge in 2018 on the Dutch Design Week, where we were first able to present the bridge when it was completely finished and to try it out to see if the sensor network worked. But of course, there was a whole history before that. But MX3D is, in short, a company that has a vision where robotics will be used more and more on the build side to 3D print either large objects or part of objects to facilitate the building and make it more autonomous, and make it more completely digital. And whether we are going to see robots printing full bridges or robots doing all kinds of tasks on the build side, that has to be seen. But yeah, MX3D focuses then mainly on the 3D printing element of this dream. So Our history is a typical one, just like my own background. The company was born out of a Dutch design agency, Joris Laarman Lab. And in that laboratory, Joris did a lot of research into new methods of fabrication and new design tools like algorithms and cut programs and so on. And his first most acclaimed project is the bone chair, which basically uses an algorithm to define how a bone structure would solve the technical problem of a chair. So how can you make a chair as efficient as possible if it was a bone structure? So yeah, we put an algorithm to work, and basically that algorithm took away all the material that was not needed for creating a safe chair. And the great thing is that you get a chair that is very elegant and very efficient. And yeah, hopefully that you also find it a beautiful end product, because yeah, algorithmic design almost automatically leads to a much more organic design as well. And this organic design is also something that you will see throughout our work. So this project is also interesting because it was the first time the company was introduced to 3D printing on a larger scale. So by this time, 2006, small time 3D printing existed. Metal printing definitely didn't. And what we did find was a person who could print the mold. So not directly the chair, but the mold was printed with cooling channels inside. So the whole chair would be casted and cooled down at an equal rate. So we continued investigation both on the digital and the making side, the production side, because it is a marriage. You can make the most wonderful things in the digital world, but if you cannot actually realize them, what's the point? So we tried the first metal printers that came around. So you have these powder bed printers. They basically print layer by layer by layer, and they can make phenomenal results, very detailed and very beautiful as well. But we did find some problems with this chair. So one of these problems was that the build volumes of these printers is relatively small. So you have to think about a big shoebox. And so for this chair, we had to cut it up in 16 parts and reassemble it afterwards. So basically you're making a very automated chair with lots of manual labor involved to make the assembly. And we thought that could be done better. So we were triggered basically to come up with a bigger way of 3D printing. So we bought an old automotive robot. We had a welding machine, and we created a bit of software with the Rhino grasshopper. And together with that, we were able to start experimenting a bit with 3D printing metal. And basically what you see here is a welding robot, but instead of printing two plates together, it just puts either dot on dot and builds geometry like this, or you continuously print layer on layer until you have your geometry. And this, as you can see, is very rough initial work, but it just proved that it was possible because, yeah, I mean, like in any classic innovation story, people told us when we said like, hey, we want a 3D print with a welding machine, they were all like, oh no, this is never gonna happen. It's gonna be too hot. It's gonna melt. The quality is gonna be horrible. And we thought like, yeah, I mean, we think it should work. So let's just give it a try. So a couple of weeks of trying gave us these results. We put everything on YouTube, and we just said to people like, hey, people, we're doing this. What do you think? And this led to so much interesting results. So instead of trying to patent it and everything, we just opened up and we created a space in which people stepped forward to help us out. And this was really important in the end for us being able to make the bridge happen, because obviously for a small company, such a project is too big to handle. But we managed to find a lot of partners with our open attitude. And also our architects and artists came along with their own ideas of what they wanted to print with our technology. So in the beginning, art was the only thing we could do, because we didn't have a clue about the material properties. We didn't know whether it would be strong enough, but at least, you know, we could see it was good for artistic purposes. But after doing a couple of these projects, we thought like, yeah, okay, this is actually too nice not to have a bigger, more constructive project. And we started to think about what would be the best way to show the world that this technology is now available for big construction projects. So yeah, what is more symbolic basically than a bridge? Everybody knows that if you see a bridge in the city center of Amsterdam and people are walking on it, then you just know, okay, these people, they know what they are doing, because otherwise the city would never allow such an object to be placed in the city. So for us, this was a way of showing people this technology was at a certain level, but on a more intuitive way. And at the same time, we wanted to show people what you could do once you have this new geometrical freedom, because of course, yeah, when you're working with standards, you're working with H-beam, I-beam, tubes, and so on. But now, I mean, there's not too much that holds you back in creating more complicated shapes. So that's also part of the design to make sure that people really understand that this is a new technology. So again, we use the topology optimization strategies to come up with our initial ideas of what this bridge could look like. And we did some analysis, but of course, every project also needs a visionary idea. And this was in 2016, an image that we spread, and we told everybody like, hey, if you want to help us, let yourself be known, and we form a collective, and we're gonna try this. And we picked the red light district, not just because it's a nice area to be, but also because the canals in this area of town are the smallest of Amsterdam. So you have to realize our technology, you know, in this phase was not so well known yet. So to make a bridge of 12 meters, that was doable, we thought. But most canals in Amsterdam are 30 meters or bigger. So we didn't want to do that, of course, with the first bridge. So we started with the design, and like we always do, without any limitations. So we made the most radical design that we could think of and print. But unfortunately, after 1 year of design and testing and so on, the city and the engineers concluded that this was not the best design for this bridge. They were afraid that if a boat would hit it, that one of these members would break, and then the whole bridge would come down. And of course, we're not bridge makers. We're more, you know, we're coming from art and design. So this was a big blow. But there was nothing we could do about it. And you all know, you know, if the city says it's not possible, then that's the final verdict. So we started working with Arab at that moment. So Arab is a global engineering company, and they helped us coming up with a design which was more sort of 100% bet that it was going to work. And that's the U shape that we create. So we created a U shape. And then we have a double folded handrail and pipes as a support. And this was a shape that both the city and the engineers, based on the material properties that we had available, believed would be safe at that time. So we started with this, and because the bridge was not exactly straight, we were able to give it a little swirl. Again, also to show the possibilities of the technology and the force lines that came about. So the blue and the red colors, they are also a very intricate part of the structural design. So you will see as well, if you look at the bridge again, you see the arches in the handrail, and in the bottom, you will also see the same structure back. So the idea is that, you know, you play around with your digital design, and because you're 3D printing, you don't really have to change anything from that concept, because you can realize the complicated shape that comes out of this original design. So here we started working with the Imperial College, and they made all the FEM models that we needed to validate whether this bridge would be strong enough. So they did a lot of material testing as well. But this modeling, we started with just an initial idea, and we kept filling it with more and more data until we really had sufficient digital proof that this was gonna work. So what this ultimately on the design side is going to lead to, we think, is that you have a lot of information, you put it in an algorithm, and then this algorithm can actually start designing its own variations, because he can decide what is good, what is safe, and can come up with ideas. And the role of the architect, engineer is much more to choose and to validate, or to give the algorithm its bounding boxes than the original design tasks that people had before. So we really see with this 3D printing coming up, you also see that digital design methods, algorithmic design is going to be more present, because you can load all the information in this digital twin, which I will mention later as well. And then within this digital twin, you can do all the calculations that you need to do for such a complex structure. Because one of the major problems we had in the beginning was that a regular sort of engineer at the building company was not able to tell whether the structure would be safe or not, because it was everything was bended, and there was just not any reference for him. So you almost need to have a digital way of doing the calculation of the strength here. So again, both the actual making technique as the designing technique are married together, and they are needed to progress together to continue with this technology. So at this time we had quite a few universities and big institutes that were on board, and as you can understand, they wanted to do more and more and more research. And at some point we were like, oh, we also need to finish this bridge at some point. So we said, okay, we're just going to print this bridge, and then you can test to see if everything works. In effect, we were all making assumptions, but in the end, you just have to start, try it, and see if it works. And for such a big project, that is of course a bit scary, but it was also very nice to actually have this project on the road. So we did a bit of the bridge with the robot on top. So you see here that the robot is actually printing under itself. So theoretically, we have proven that is possible. But in practice, you see also the cages here on the side. We printed large elements of the bridge on multiple robots at the same time. In the future, robots printing bridges completely autonomous, that is going to be possible without doubt. But in this initial project, we did have to take some steps that were a bit easier to make it all possible, because there's so much complexity here in the project that you want to find some easy ways every now and then. But of course, one of the major questions that we had to answer was, is this bridge safe? I mean, in the beginning, when we first did our testing with the robot, everybody was like, okay, this is just going to be so bad quality because it's weld on weld, and the connection is never going to be good. And but in the end, we've done a lot of research, and the material properties are almost always above the benchmarks of the welding wire or of the material itself. It is a different material, so it is not the same as cold rolled steel or something, but we do have enough information now to understand how it's working. But of course, this took a lot of testing. So at the college, they crushed more than we liked. I mean, we had to bring them pallet loads of samples, and they crushed this. And at some point, there was more than enough information to make the next step. So here you see that team. They censored the whole bridge to see what the effect was of a 20-ton load. So we came up with 20 ton. It's like the maximum design load times 2. And then we said, okay, let's just put it on there and see what the bridge is going to do. And this test allowed us to prove to the government that the bridge was safe, because the bridge was behaving exactly like we planned. So the calculation models that we had by then predicted a 2.5 centimeter movement of the bridge downwards if the load was applied, and this was exactly the result of this. As you can see here, the whole bridge on the side has all the dots, and that's a camera is holding it, and it's actually viewing what the displacement of the whole bridge is. And more of these interesting technologies were used to really map the behavior. But this sensor network that you just saw, that was a very rudimentary start of what became a very intelligent sensor network that we now have under the bridge. And what this sensor network basically does is it has 4 load cells and a lot of accelerometers and other sensors that show how the bridge is being used. And this allows us to understand how such a big monolithic 3D printed bridge is actually behaving. I mean, one of the questions that we had is like, okay, if the sun is on this bridge, but only on the half, how is it going to deform? I mean, it is going to deform, but we just don't know how. And this sensor system allows us to get all that information. And the Alan Turing Institute that we work with, they make a digital twin of all this information. So by now we start understanding how this bridge is actually behaving in real life. And the digital twin is then going to be used for a research into new possible designs. So what we can do with a digital twin is not only for BIM purposes, for instance, but it's also an experimental tool where you can say, is like, hey, what's going to happen if we reduce the wall thickness of this bridge with 1 millimeter? Or what is going to happen if we take out this middle part, which we think is not necessary? And we can have the digital twin do, again, the calculations to see whether it can come up with a more efficient bridge. As you as engineers can probably all see, this bridge was made pretty firm. After the first design failure, we said like, okay, this time it has to be right, and we do not want to have another rejection. So we applied a heavy safety factor. But of course, one of the big advantages of this technology is that you can actually reduce quite a bit of material. So for 3D printing, to explain, if you have an H-beam, it's much more efficient just to use the whole beam and put it there and have a heavy beam, but it's fast and it's cheap. But if you 3D print a similar structure, you actually want to reduce the material to the absolute minimum, because every kilo that you produce takes time. So you don't want to produce any more material than absolutely necessary. So in the whole 3D printing philosophy, as you can say it, it's essential to reduce the amount of material that you use, because then you can go faster. And this is also why I think that 3D printing, it will take quite a bit of time before it becomes more mainstream, especially in building, which is conservative and also cost effective at the moment. But after people really see the benefit of this lightweight printing, you will see new applications that probably we don't really understand yet. And I think that's also from our perspective the most interesting is that we are creating a technology that, we are creating a bridge now with it, but probably that, in 10 years time, we'll see what the real applications can be. So we're looking forward to all that new development as well. So yeah, as soon as we had it finished, the police in the Netherlands, they said, okay, let's test it out. So even before the opening, they just rolled over with their police motors, and well, it worked. So then we were ready for the opening. Yeah, I mean, it took 5 years, I guess, but this July, finally, I had to come back from my holiday. But finally, we were able to open it. It's a complex area in the city to do that. But we were fortunate enough to be able to arrange the Queen of the Netherlands to open. But actually, she didn't really have a job because the robot was doing the ribbon cutting. So we did have a bit of a scare during the opening. The ribbon was going like this. And of course, robots are in general really stupid, so they don't really know what's happening. But fortunately, the wind just died down a little bit, and everything went according to plan. But yeah, for us, you also see our collaborator Joris here on the side. For us, this was really a big relief after 5 years working on such an enormous. Yeah, MX3D is also in a way a bit liberated now, with doing all kinds of other projects, which are equally important for us as a company, but they now have get the time and the attention they also deserve. So to give you a couple of ideas of what we've been working on, we've been, for instance, working a lot in the tooling industry, where one of the projects we did together with the robotics manufacturer ABB and Altair is to see how we can replace parts. So you have a 20-year-old robot, part breaks down. If you want to have this part made somewhere, you probably don't even know where to start. With this technology, we see that you can make the same part in a couple of days with less material in your own mini casting factory. So, for instance, a mining company, which is a more Brazilian example, perhaps, you're far away, you need a spare part. If you don't have that spare part on site, this is going to cost you dearly because you're going to be having downtime. So this technology will be able to be used in this kind of heavy industry kind of areas, where you can just have one or two of these robots available. They can do other tasks when they're not needed, but as soon as you need spare parts, they can start printing, and you at least have a maybe intermediate part until the real replacement comes, or this becomes the real replacement. Just to prove that it actually works as well, so we reinstalled it back into our robot and made it move. So yeah, you see here as well, we used 50% less material for making this arm than the original part. And again, one of the examples, it's also a nice reduction in footprint of such a part, of course. So with Takanaka Corporation, in a Japanese construction company, we explored how this technology can be used in connection nodes. So basically, if you make a Zaha-Hadid complex steel structure, everything is parametric, and the connectors are horrible to make. I mean, if you even still have the skilled workers that can make these connectors, it's going to be a specialistic work, expensive, and maybe a reason why the structure is eventually not built. So with this technology, we envision that you create the structure, and the nodes are automatically printed with a machine like MX3D's, and then complexity is not so much of an issue anymore. So you don't have to make complex molds and have a very good welder anymore. This can all be automated. We even added some spaces in there for, I mean, if you imagine this would be a huge connector, it's always good to have some concrete in there as yeah, I think it's a fire retardant, but also as a stabilizer. So this is something that we explored, and we're now working with them to apply this in a real building. Well, in Japanese, things take a lot of time, but let's hope in a couple of years' time we can actually realize this together with them. But we do a lot of research on the background to realize this project now. So here you see the final example. So obviously this is again an early prototype of what it could become. So maybe we can find more efficient, faster to print notes ideas in the future, but this was one of our initial ideas there. Yeah, and then also we have to take it to the next level. And what we did is we gathered all of our information, all of our learnings into a new machine. So we created our own 3D printer. We added a group of sensors. We created our software to make the printing possible. And we're now allowing other companies to print like this. I mean, we see there is 6-7 markets maybe in which a technology like this could find a place. And for a small company like MX3D, that's too many markets. We cannot dive into all the potential use cases. So we decided to become a technology provider. Yeah, so some of the work we've been doing with that is also with the Schindler elevator company in Switzerland. That's where the main quarters is. So we keep on trying to figure out together with corporations what the use case would be in their company. And at the same time, we inspire, hopefully, at least other people to also start thinking about, you know, what could this mean for me? How could I apply this? And by staying open like this, by telling people what is possible, we hope more and more ideas come up. So yeah, we were also the more boring things. Maybe what we do is we do a lot of European projects, which are in fact not boring. I mean, but they're just not so visible as a bridge, for instance. But what we do in these projects is really to work together with all parties, in this case from Europe, to develop the whole workflow from cut design to a certified end part. And we research every step that you have to take to make that happen. Because of course, you know, yeah, you can print the most beautiful parts or bridges, but if you cannot have it certified, in the end, it's not a business case technology. So this is something that we've been working on a lot. So you see the quality there is a bit bad, but in the next month, we will announce that the cell is certified, and in 2 months' time, we will add some certified materials there as well. So this will allow us and our customers to print certified parts directly, and this is a huge game-changing step for us and for the clients. Because it means that anything you make with these materials can then most likely be much quicker be approved. So yeah, I guess this is one step away from the pure innovation. We're now at the phase where you know, new entries don't have to do all that initial work anymore, but they can really start thinking about the real business case for them. And that's also what we work a lot more on nowadays with other parties. So yeah, I mean, MX3D is a company with a vision. So this is the vision that we set ourselves. We were like, okay, why not, you know, create a robot that prints difficult shapes, maybe in space or in difficult locations here on Earth. So we're working on creating our robot and making it fully autonomous. So that all the potential interventions that have to happen during the print process are also done by the robot. And this has a couple of big advantages. So one is that everything is digital, even the small interventions. But two is that you don't need manpower anymore to build something. So even though 3D printing in metal is maybe not the fastest technology. I mean, we can print between 1 and 4 kilos per hour, but if it's fully autonomous, you just put it in its cage, you lock the door, and you come back a month later, and your part is ready, without any significant personnel costs. I mean, that's quite interesting, especially because you can create shapes that before would be impossible to make. So you can achieve a higher complexity in your parts, fully controlled by a digital method, and at the same time without too much skilled labor needed. In Holland, at least, I mean, welding personnel with the international welding certificates. I mean, I think there are 3 people here in the Netherlands that can do that, and they're really hard to find and definitely hard to sign as an employee. Completely automated welding is definitely the future, I think. So to make this breakdown, this dream, we already started, and we were happy to be able to announce it last week that we had a collaboration together with ESA and some architecture group, but ESA is the European Space Agency, and we worked on the Lunar Habitat. Created a lunar habitat sphere, and in that sphere they wanted to use as much lighter weight structures as possible. So we used a topology optimization process. Again, it's getting boring, but this is what this technology does, to reduce the weight and to make a more complex structure, and use that as part of this lunar base. So this is the latest project that we have to offer, and I am pretty sure that we will be able to make the next step. So in 2025, we'll do something exciting like printing in space, or printing somewhere in the desert, and fully autonomous. And if you have any ideas like this, or if you want to collaborate, we're, as you see, always open for such collaborations. So I will be happy to hear from you. Thank you.
Okay. Thank you very much, Mr. Van der Velden. It was such an honor to hear a little bit more about how you achieved that incredible goals. Now we have some questions here. I don't know if you have enough time to answer all of them in the last 15 minutes, but let's do the possible. Here, João Carlos. Oh, you have lots of compliments here. It's incredible, the technology you developed. You know, you are in the high level of technology in the world. João Carlos is asking, how big is the challenge of having robots or printers of sufficient scale for giant structures, like a large bridge or other structures? And would that be possible to achieve that?
Yes, I mean, in principle, it's possible to print with one nozzle something like 10 kilos per hour. And if you imagine a machine, whether it's a robot or a multi-tool machine that can print at the same time, you could have deposit rates which are quite impressive. The question is, if you have a big bridge, maybe the thickness of the bridge is going to help. So if you want to build a very thin wall structure like the bridge, it's maybe 4 millimeters at some points, or 3. Then you have your deposit rate is just not going to be much higher because of all the heat that you put in. But if you would have a very thick, shaped bridge, you can probably go quite a bit higher. So there is a lot of room for improvement, but it depends on the end application.
Did you use any cool system when you were printing that bridge?
We tried quite a few, but we decided not to use anything. So the material properties are not necessarily better if you cool them with air or water or whatever technology you want to use. So we decided to create more intelligence in the production. So we put a lot of material on the build plate, so that by the time you would come back to the first point, it would be cooled down sufficiently, so you don't have any waiting time.
Okay. Paulo Assis is asking if you have any plan on expanding business to Brazil, and which will be the problems to export 3D printer or raw materials here to Brazil.
Well, we do business with everybody in the world, so we don't. We definitely also would like to come to Brazil. We did have one attempt for collaboration with a university and a company in Brazil, but I do have one strange memory that there was something like a 50% tax or something on top of our service. And that made it quite hard for them to hire us because it became very expensive. But in effect, what we do is using a welding robot with some software. So there's no technical barrier to apply the same thing in Brazil, and definitely open for that.
How long did it take to print the whole bridge? Marshall is asking.
Yeah, good question. So we took about a year for printing, but we did some other projects in between. And when you use 4 robots at say 1.5 to 2 kilos per hour, you need 3,000 hours of printing. So theoretically, you can squeeze that with 4 robots in 1.5 months if they print continuously. I would say if we would have to do the next bridge, we could probably print it in 4 months' time, 4 or 5 months' time. And then hopefully the next one in a little shorter, and the next one. So.
I saw in one of the pictures you showed that you used abacus to calculate the bridge. Sorry. But Marcio is asking which were the other softwares used to create the 3D model?
Yeah, we use, so Abacus is more our partner, Imperial College, but we use mainly Rhino and Grasshopper as the base cut software. And then, we use our own COM software to prepare the geometry for printing. Okay. So, but Rhino Grasshopper is really for parametric design, is by far the best program, we think. I don't want to make a commercial of it, but.
What was the motivation for the twisted profile of the bridge? It has a motivation in terms of structure or just a design choice? Luis Felipe Franco is asking you.
Yeah. So there is a couple of reasons. So one of the reasons was that the city came up with a very curious twofold demand. So on the one side, they want the bridge to be as wide as possible, and on the other side, a car was not allowed to pass the bridge because it is not calculated for a car. So they said, if it is wide enough, you have to calculate it for a car. So by making a twist in the bridge, we made sure that a car would never be able to actually pass the bridge, and we could still keep it a bit wider. So it's a bit of a quirky reason. And the second one was that the 2 bridge heads were not exactly across each other. So basically they were a little bit like this. So we said we can either use a straight line from one end to the other, but we can also just twist to it. And obviously we like to do that because it shows a bit what you can do, and because this was not like it didn't have to be the most efficient bridge in the world. This was the showpiece bridge that shows what is possible, and that's one of the reasons as well.
Okay. Emilio Cavamura is asking, did you think about using two materials in the bridge fabrication process, like reinforced concrete and steel or something like that, or not?
Well, to be honest, doing it in one material was already really complex. We were really happy that we were able to come up with enough knowledge about the behavior of this one material that we were not considering other materials. But obviously, in the future, so we believe in hybrid printing, which means as much as that, for a bridge, for example, you the standard steel beams are not going to be printed because you can better just order them at Gerdau or ArcelorMittal. And then the special connectors is something that you would print. And yeah, and the same goes for concrete metal combination. I mean, it is possible, but it is the next step, I think. And
okay. Now, Paula sees again, how can engineers in the industry prepare for 3D printing still? Acquiring some skills on FFF with plastics would be a good start.
On well, FFF, I
think it's fused filament fabrication. Yeah.
Okay. Yeah. I call it FDM. There's a fused deposit modeling, I think. Okay. But yeah, I mean, you know, if you have an Ultimaker or MakerBot or whatever it's called, and it's in your office and it's printing plastic with a filament, that is in effect, it is the same as what we do. I mean, we have a little bit more freedom because of the robot, but it definitely gives you an idea. So if you can make something with this plastic printer, you can maybe also make it, or probably also make it with this technology. And indeed, that's where it has to start. I mean, if you do not start with your design thinking about 3D printing, then it usually is never going to work. I mean, if we get people that say like, hey, we want to 3D print this, and it turned out to be a completely conventional design, it is usually just either not worth it to 3D print it, or completely illogical because it can be made different. But if you start with the idea is like, okay, I don't have these boundaries that I usually have because of the 3D printing, what would I make? If that's the way you start, and you keep in mind, you know, between 8 and 10 millimeters wall thickness, and not too much overhang like with the filament printing, then yeah, you are on the good track for a design for metal printing.
Well, before going to Nelson, to the closing, I would like just to thank you very much. It was a pleasure to have, an honor to have you here. I think most engineers here in Brazil were really wondering, how did you do that? Did you achieve that? The news that you 3D printed the steel bridge were worldwide spread, and it was not different from here in Brazil. We received that in WhatsApp, you know, in lots of groups. Oh, that's a big achievement. The photos of the Queen of the Netherlands there. And thank you very much to be here. Okay, Nelson, please, your final word.
Mr. Van der Velde, thousands of thanks to you, because there's innovation and this disruptive innovation that create a large perspective in our industry, in our world. We can extend our imagination where we can apply this technology. That's a wonderful solution. I suppose that we are amazing about this. We don't know how to explain how successful I will be with your speech. Thank you, Mr. Van der Velde. Your final words, please.
Well, thank you very much for the chance to hopefully inspire you to think about either this kind of innovation or any innovation that you could achieve within your profession. Yeah, as said, it's sometimes just a question of having a good idea and trying it out and seeing whether it works. And who knows, the next bridge we're going to see in Brazil. So I was happy to be here, and I wish you a good working day still.
Thank you.
Thank you. Thank you.
Thanks.
Applause to you. Applause.
Congratulations. A wonderful speech. Thank you.